Alright, so today we're going to be talking about inverse functions. Wait a second to get your notes. The concept of inverse is actually pretty straightforward, but we're going to be learning about how to apply that concept to a couple different representations of functions and relations. So you're going to see tables with points, you're going to see equations with y equals, you're going to see some functions with f of x equals. We're going to do the same kind of thing for each of these different contexts. Sorry? The number is 116. Oh, that piece of paper that was on your desk when you guys walked in, just make sure that you fill that out for your parents if they're coming to that school night so they know where their first class is. Alright, so a little bit of vocabulary class notation to begin with. So inverse function notation looks like this. Now that looks an awful lot like an exponent, doesn't it? Looks like f raised to the -1, but that's not the case here. Usually when you guys are using an f, that represents a function, not a variable. This would be an exponent if it was a variable, but f is not a variable. We use that as a abbreviation for function. So it's not f raised to the -1 power. It's not that. Okay. Instead, it's just saying that it's the inverse of function f. So just be really careful distinguishing those two ideas. This is a very important concept, so I'm going to star it or highlight it or underline it. I know it's already in a box, but it's the most important box on this page. The reflection of a function over line y equals x represents the inverse of the reflected function. This is the definition of an inverse. Do you guys remember from geometry when you guys reflected over y equals x? Anybody remember? Y equals x is a line that looks like this. It has a slope of 1 and it goes to the origin. If you guys reflect over that line, do you guys remember how you do that? Switch the x and y. So we're basically doing, that's the idea that we're working with here. Switch x and y. That's our basic concept here that goes with this last box. When you guys reflect over y equals x, what that does is it takes the x and y values of your function and it inverts them. So that's our main concept that you're going to see happen over and over again as we go through this process. So let's start with the easiest one first. If you guys are given a set of ordered pairs, whether it's written like this or in a table, all you're going to do is switch x and y values. That's all you have to do. It's very simple, very straightforward. So let's say we start with example number 1. Our first point was 0, -3. What would our inverted point be? -3, 0. You don't know what our 1, -1 can do. -1, next one. 1, 2, next. 3, 3, next. 4. When you guys have just a string of numbers, if they're in ordered pairs, you're literally taking the definition of reflecting over y equals x and apply that, especially x and y. Same thing in table values, just a little bit more organized. So if the first point is 5, -7, how would I invert that? I would just switch the x and y, now they're kind of upside down, and you would do that for every row. So you basically took the top row and the bottom row and you switch them. Alright, go ahead and try the last one. They're in columns now. Go ahead and see if you can figure out what that new table of values would be for the inverse. Alright, what would my first row be? Next one? Next. So everybody can agree this is pretty simple, right? So if you guys see ordered pairs or table values, that is how you would find the inverse. What if you're given a graph? So let's say instead of being given the points on a chart or with a set of ordered pairs, instead you're given the graph, the representation of that. So what you're going to do is find 3 plus, that means 3 or more points on the graph. And then switch x and y. So we're doing the same thing that we did in the example above, but we have to do one extra step because they haven't given us points. We have to find them for ourselves. So you're going to take the graph, and I have in a little bit more detail here. Write down some of the points from your graph. You want at least 3. You're going to rewrite the points using the inverse process of switching x and y, and then re-graph those points. So that's how you guys would graph an inverse. If somebody asks you to graph an inverse, you have to find the points first and then stick them on the coordinate plane with the original picture. Yes.
If it's on the axis, wouldn't it just be the same point?
It depends on where on the axis. It would only be the same point if both the x and the y are the same number. So let's say I chose this point, and this point. Let's say you pick any 3, but you want them to be a little bit spread out. You don't want them too close to each other. Let's say I pick those 3. So that would be -1, 2, 1, 0, and 3, 2. Everybody agrees that I can't write something starting again. Those numbers are accurate. Okay. So let's say those are the 3 points I choose. What would the inverse point be? Okay, go ahead and graph those. So I have 2, -1, 0, 1, and 1, 2, 1, 2, 3. Those are where the points are. Now what shape did this make? Or what shape was the original? It's like a V, right? Okay. Which one of these red points was the point, the corner of the V? Which one of these red points was this one? I'm going to put a little star right here. It's really important to know where particular details are in the graph so you can replicate that accurately on the inverse. So 0, 1, sorry, 1, 0 was the pointy part of the first graph. That means that this point has to be the pointy part of the other graph. That's right here. So your new graph is going to look like this. I have all the points lined up so you can see which points correspond to each other. So it's really important you do that so you know what orientation the graph will look like. So if you guys remember, the line y equals x is right here. So if you reflect it, it will flip over on its side. You can visualize that line of reflection by yes, you should write it that way. You do want the middle point to be the central location, right in the middle of the graph, so the other points kind of stand out. It's a really good strategy to use. Okay, everybody clear with that one? Okay, next, let's pick some points. I have this one, I have this one, and I have. Pick exact points. You don't want decimals. That would just make it way too complicated. So pick points that are at exact intersections of the crosshairs of the coordinate plane. So what are those points that I chose? 0. What would the inverse point be? So, John, that comes back to what you were talking about. These points will remain the same if both of the 2 values, x and y, are identical. Okay, so let's go ahead and graph those. I'm going to use different colors. I have 0, 0, and 1, 1 still, but what's my new point? 2, 1, 2, 3, 4 here. So my graph is going to look like this. And remember, the line you guys are reflecting over is this line right here, so it should make sense that it flips over like that. Okay, what are some of the original points? Back. Everybody else, what are the inverse points? Next. Okay, so once you write those down, you're going to graph those. So these 2 points, or that puts us in saying you go 1, -1 is here, and 1, 2, 3, 4, 1, 2 is right here. So your graph will like that. And again, you're reflecting over this diagonal line, so it should make sense that it flips over to that corner. Alright, so you guys will need to be able to do this kind of thing too, not only find the inverse points, but then graph them and kind of illustrate why that's the inverse, the reflection over the y equals x. Questions on the first page? Alright. Situation number 3, if you're given an equation, no longer will you guys have x's and y's visually represented for you. Instead, you guys will have an equation. And I have these 2 separated because this one starts off with y equals and this one starts off with x equals. They're almost identical. This one just has one slight extra step. So basically what you guys have to do is switch X and Y, then resolve for Y. So you're still doing the switching, so switching X and Y, but for us right here, they're variables. So you're going to switch variables X and Y, you're going to rewrite the expression, switching where the X and Y are, and then once you've done that, you've jumbled it up, so now you have to resolve for Y. So for instance, I have Y equals negative 2X minus 10. How would I rewrite that if I took the X and the Y and I switched their positions? Okay, so I'm here. Now I messed it up, right? Anytime you guys have an equation, you want it to be Y equals. So when I do this, I switch the X and the Y. Now I have to resolve it for where the Y is now. So what would I do first to solve for Y? Add 10. And divide by negative 2. So this right here, that function, once you switch and then resolve, this is the inverse of the original. You guys see the connection on see how it was subtracting? I was subtracting 10 in the original, but now it's adding 10. See how it was multiplying negative 2, now it's dividing negative 2. So you'll notice how all the original operations will switch on their heads and go to the inverse operations to create your new function. Now, I want you guys, I'm going to be super picky about this, I want you guys always to write your final answer for an inverse using inverse notation. Remember on the very first page? Alright, this little bit, I'm going to write it on both sides of it. Always write your final answer like this. Instead of writing Y equals, you want to write F of, or sorry, not of, F negative 1, which is your inverse notation, and then write what the final is. So your final answer should always have inverse notation. F negative 1. Alright, does everybody follow how I did that? Cool. How would I do the next one? Always start by switching X and Y. That's the easiest part. We saw that in both of the examples on the previous page. Then what would I do if I try to solve for Y? Got 3. Divide by negative 1. I'm just going to change everything signs. If you divide by negative 1, this positive becomes negative, that negative becomes positive, and this is positive. You cannot take square roots or cube roots or any type of root actually if there's a number in front of the variable. So you need to make sure that you get rid of any coefficients, whether it's negative, positive, whatever it is, you need to divide that away. And so I just rewrote it using those lines. Now what would I do? Now I can cube. Everybody knows what cube root is, right? Okay. Then how would you represent your final answer? That's negative 1 equals cube root. Okay. Now I'm going to let you guys try the third one on your own. You guys are doing great. Hopefully, did everybody get at least that far? Okay, then what would I do? When you guys are solving algebraically, you kind of want to think about doing the order of operations in reverse. You want to take everything away going from the outside in. So what's the first thing that I would do? Subtract 2. Right here. Okay. Now, can you distribute that square? No, you cannot. Never distribute squares. Can I subtract a 1? No, it's stuck inside the parentheses. The order of operations is go from the outside in. When you're solving, if the square happens before the plus 1, so what would I do? Square root. You're going to square root both sides. Give me this. So now you can get rid of the parentheses and the square. So take care of those. Cancel away with the square. Then what would you do? You subtract 1. Now when you guys are writing something like this where you have part of it is in a square root, part of it's not, when you guys subtract the 1, would it subtract with the 2 that's inside the radical? No, this is protected by the house, right? The radical house. That's all by itself. Negative 1 is not really going to affect anything that has to do with that. So you guys are going to write it like this, usually. That's the best way to write it. You have the number in the front, and whatever sign is going on, and then the radical next to it. Okay? But I do have something that I need to point out, and you guys may not be familiar with it. You guys take the square root. How many is this? If I say square root of 4, what would you say? It's 2? You guys have been doing math growing up in the past. And I ask you for a square root, you typically just get one answer. That's incorrect. There's always 2 answers to a square root. And when you take the square root, you're finding a number that you can multiply times itself to get that number, right? So when you take the square root of 4, you get 2 because 2 times 2 is 4. What about negative 2 times negative 2? And also 4? Yeah, so whenever you guys take a square root, I don't know why they teach it differently when you guys are younger. When you guys take a square root, it's actually both the positive and the negative version of the answer you would get. So for algebra 2, it's very important when I ask for the square root of something, if I say what's the square root of 4, you guys will say 2 and negative 2. You guys have to train yourself to do that. So you're going to see this symbol show up a lot in algebra 2. It's a plus minus. It takes those two things and kind of combines them together. Anytime you guys are taking a square root, you need to include that symbol. Okay. Your final answer would be that negative 1 equals to negative 1 plus or minus the square root of x minus 2. Okay. So anytime you guys use a square root symbol thing, solving, plus minus symbol needs to be in front of it. Positive and negative. Alright, any questions on any 3 of those examples? Right. The next section is going to be very similar, but before I move into that, I want you with a shoulder partner to pick one of these 3 questions. You're going to go resolve it verbally with the person next to you, and then you guys are going to switch roles, and then your shoulder partner will explain a different one to you. So each one of you is going to pick one of these problems, your favorite, and explain it to your shoulder partner, and then switch. Okay, go ahead and do that real quickly.
Oh, yeah,
All right. Do you have any questions arising now? That is good? Yes, good. Yes. So anytime you're using a square root, particularly in a solution kind of process with an equation, you need to include the plus minus. Before you would have just left it as positive because that's what you guys knew. But now that we're in algebra 2, you need to be aware it's both positive and negative, so you have to include that symbol. Alright, now we're going to do type number 4, as you guys are given a function. So this is exactly the same as what we were doing before, plus one extra step. So rewrite f of x as y y. Right, because our process is to switch x and y, and if you don't see a y, you won't know what to switch with. So just rewrite the f of x notation as y, and then do the same as above. I'm not going to rewrite the steps. They're printed already for you. So if you guys are given f of x notation, just switch it to a y really quick, and then do the exact same thing that we did above. Okay? So I'll do one of these with you, and you guys will do the other two on your own. Which one of these three would you like me to do with you? Second one? Okay. So I'm going to go ahead and this process, well, I'm not going to use x and substitution. I'm just going to scribble this out and put a y instead. So it's visually easier to work with switching x and y. Alright, so I would first switch the x and y, so it looks like this. Over here. Everybody with me? Alright, what would I do first? Multiply by 3. Again, you're trying to solve from the outside in, so the first thing you want to get rid of is the fraction. So it becomes 3x equals that. Then, this is a square root, right? How do you cancel a square root? Square both sides. So when you square this side, now remember how I said over there you can't distribute a square if there's an addition or subtraction between the two things, right? If they're multiplication, can you distribute the square? So if I'm squaring this entire thing, what do you think it would turn into? 9x squared. So anytime you guys are squaring something that has a coefficient, there's no addition or subtraction, you're going to square both of them. So 3 squared and x squared gives you 9x squared. Is everybody okay with that part? Okay. If you leave this 3x squared, you forget to square the 3, it's going to mess up life. Right, now what? Subtract the 1. Divide by 3. Instead of writing y, I'm going to write f negative 1. Then x squared minus 1 divided by 3. Questions? Yes. You have to square both sides. So when you square both sides at the same time, all the way at the end, you should write your notation and then answer. 2 divided by x. There are some situations where the inverse and the original function are exactly the same. So for this one, you would switch the x and y. You would have anything that's in the denominator of a fraction, you have to multiply that over to get rid of the fraction. So you would move the y over like this, but then to get y by itself, you'd have to divide the x, and you just get back straight here. So that's possible. You can have the inverse be exactly the same as the original. Don't get confused if that happens. And then over here, when you guys are solving, you should end up getting, don't forget your plus or minus, a giant square root with that entire fraction in front of you. Because remember, you do order of operations in reverse, or from the outside in. So you do add the 3, divide by 2, and then take the square root with the plus or minus. Anytime you draw a square root symbol in the equation, there should be a plus or minus. Okay? Questions on any of those things? All right. So that was our first learning target. So just to recap, so I can find the inverse of a function that is represented in several different forms. That would be points. So you have points or a table. You guys have a graph, and you would graph the inverse, or you guys have an equation. Is everybody okay with all three of those? Yes. Okay. Our next learning target then is to determine if I give you two functions, to decide if they are inverses or not. Now the way that you would do that is if you have f of x and then f negative 1 of x, so the original and then possibly the inverse, they're going to be inverses if you guys do composition twice and you get x both times. So the two compositions we're going to do is you're going to plug the inverse into the original, and then you're going to plug the original into the inverse. So you're doing both directions. If you get x each time, then they're inverses. You get x for one and then like negative 2x plus 3 for the other. Those are not the same values, they're not going to be inverses, right? So This is why we learned composition a little bit early on and practiced it a little bit more, because you need composition to do this first one. Okay, so let's go ahead and do, so we have these two functions. We're going to do f of g of x and g of f of x. I have to do both of these. And I want both of them to just be x at the end. If they're both x, then they were inverses. Alright, so for this first composition, what's the input? G is the input, f is the original function I'm plugging into. So I'm going to write f, 1/2 x plus 5/2, and I'm going to circle x. Remember the one on the left is what you write, and then you circle. Instead of writing x, what would I write? So in parentheses, 2x minus 5, close parentheses, and then finish the rest of your expression. Everybody with me? So far? This is composition, yeah. Now what? Distribute. So if I distribute 1/2 to 2, they just cancel, right? 1/2 and 2, they cancel each other, so it's just x. And then if I distribute 1/2 to -5, I'm going to leave it as a fraction. So I distribute the 1/2, and I have this situation. What happens when I have -5 halves and +5 halves? They cancel, leaving me with x. So awesome. The first one is x. Just because the first one is x is not guaranteeing the second one is x. So you can't just stop there and say, yay, they're inverses. You gotta do it again, but now we're going to switch the direction that we're doing decomposition. Okay. So now I'm going to have g 2x minus 5. G is now my base function. I'm going to plug f into that. So instead of writing x, what would I write? I write f, right? What's f? 1/2 x plus 5/2, and then don't forget to finish your actual expression. Alright, now what? Distribute the 2. 2 times 1/2, cancel. 2 times 5 halves. The 2 here cancels out the denominator of this fraction, leaving me with just 5. Make sure you know how fractions work when you multiply like that. And then what? 5 and -5 cancel, you're left with x. So we're f of x and g of x inverses. So if you get x both times, you're good to go there. Alright, I will do one of the next two with you, and you will do the one that I don't do by yourself. So which one do you want me to do with you? 3. Okay, cool. So for 3, I'm going to do f of g of x. F of g of x and g of f of x. I'm going to do the inverse twice, switching which one's the input, which one's the base function. Alright, so if I'm starting with this one, I'm going to write cube root of 2x. But in my base function, instead of writing x, what am I going to use as the input? I'm going to use g of x, which is 2x. Now, like this. Now, how do you that up a little bit? Cube root of 4x. Now, from here, can I simplify this? So the cube root and the x cubed cancel. So how does that work? Is the 4 a perfect cube? Can you take a cube root of 4? No. Anything that's not a perfect cube cannot come out of the radical. Say it one more time? Okay. Yes. X cubed is a perfect cube, so that's left math. Anything that's a perfect cube can come out of the radical to simplify. But because 4 is not a perfect cube, that can't come out of the radical, can't simplify. So this is what we're left with. So after doing the first composition, what are we thinking? It's not going to work, right? What was the result supposed to be? X, right? So if you do one of the compositions and you don't get X, is there any point to doing the second one? No. So these are not inverses. You don't have to bother doing the second one if you don't get X in the first composition, and move on to the one. Okay? Now, go ahead and do the second one, the one right in the middle. See if we get a yes or no for that one. Glad you guys. Alright, what would my first composition look like? Yes, ma'am. Alright, did everybody get this far? You write the base function, circle the x, swap that out for whatever the input is. Right now. Hold on. Do something first. These two can still work inside of the radical. Just simplify that before you actually work with the radical symbol. Okay. So the first one we're good. Everybody get x for the first composition. Okay. Now what? Okay.
Alright, so do you have that picture of this one? And then, so we can then just do x minus 4 plus 4.
You mean square root of x and 4? Okay.
Then add
You're missing something really important. Is this what you wrote? You're missing this.
oh,
Anytime you have something attached to the x, you know over here there's nothing attached to the x, we didn't use parentheses, but here the 2 is attached to it, so if there's a square or a power or a coefficient, you need to use parentheses, okay? So you can't forget the square. So you plug in f of x where x was, parentheses, c squared, and then what would you do? What happens here when you have something that's in the square root and you square it? It cancels, right? The square and the square root cancel each other because they're inverses. Now we're just left with this. Okay, but I need to see, I'm not looking at first, I need to see it each step. Now what? The negative 4 and the positive 4 cancel, so I get x for this one. So are they inverses? Good. Very good. Alright, does anybody have any questions about this? This was our second learning target for today, being able to determine if two functions are inverses. Any questions? No?